Thank you, Matt. So I'm going to talk about profit inequality for matching, and it's a joint work with Hongao Wang, who is an undergrad student currently visiting Nanyang Technological University. Unfortunately, he cannot make it to EC because of the visa issues, but instead of him, you got his picture on a horse. All right, so usually, when I talk about profit inequality, I would like to, introduce this basic setting. But since we're in this session on profit inequality, I'm going to skip on that. Otherwise, it will get pretty repetitive. So instead, I'm going to talk about applications of profit inequality and how we, our community came to like it, so much. So it's mostly motivated by the applications in mechanism design. The first line of work was on revenue maximization or like pricing. So it's all started in 2007 with HKC paper, and then people obtained pretty impressive results for multidimensional mechanism design problems for unit demand buyers. Just one remark to make about this line of work is that the approximation constants people got there are actually significantly larger than the one in the basic profit inequality they use. Another line of work, which is much more recent, is on combinatorial auctions, but in the Bayesian setting. So it's started in 2015 with this FGL paper. And just a couple of remarks to make on this line of work is that people use pretty simple forms of profit inequality and really some simple additive thresholds. And the approximation they achieve with these thresholds is really matching the basic profit inequality. Like FGL paper gives approximation of 2. So follow-up work in this both lines seeks extensions to general feasibility domains. So if you look at, there actually has been quite a few papers after that. So they, also extended the existing results, but they always, try to do it in the spirit of general feasibility domain. And it was largely inspired by the work of Kleinberg and Weinberg in Stock 2012. So they actually developed this pretty general profit inequality for intersection of K-matroids. It's a really general set system. It captures a lot of different scenarios. And well, our community, of course, went on a quest of making it even more general, has done it for polymatroids, also extended it to some other online settings with this contention resolution scheme, did it for downward closed environments, and it's really impressive body of work. But you can see a trend here that people study pretty abstract and general settings. And by necessity, they have very complex and general purpose methods to achieve this constant approximations for these general feasibility constraints. However, you may wonder, what do we know actually about really basic settings? And specifically, let's say matching in bipartite graphs. It's one of the basic settings and central settings for our community because, there is a parallel session on matching going on right now, for example. So surprisingly, for this very basic settings, the results are not as good as we might hope them to be. So KW paper actually would consider it as an intersection of two matroids, one matroid per each side, and their result would imply like 70% approximation to the profit. This approximation could be slightly improved by the contention resolution paper to 18%, and actually both algorithms, online policies are quite complex. They are highly adaptive and updates threshold policy based on the previous history. All right, so let me actually introduce the setting. It's really simple. So we are talking about matching in bipartite graphs. So we have two parts, left and right. And I'm gonna use advantage of animation and do online algorithms, with animation. So elements here are edges in this bipartite graph. They arrive one by one online, and each edge has a weight W. Each edge can have different weight, and we're interested to select a subset of edges which must form a matching. So all feasible sets that we can select eventually must be a matching. So we are talking about online Bayesian selection problem, which means that the weights are drawn independently from some distributions, and this set of distributions is known in advance, so we actually know the set of edges that are going to arrive. We know from which distributions the weight's going to be drawn, but we don't really know the order. So the online algorithm sees edges arriving one by one. Let's say he sees this blue edge, which is distributed according to Bernoulli 0, 1. So we flip a coin. Let's say it turned out to be 1. So algorithm observes the weight and then needs to make an irrevocable decision whether to take it or not. So let's say since we're expecting a bit higher rewards in the future, algorithm decides not to take it. So then another edge arrives, we see the realized weight, we decide, let's say, to take it. Then maybe another edge with even higher weight arrives, but now we cannot take it because otherwise we would get infeasible set of edges. So we have to reject it. And finally, let's say we take the last edge no matter what. And the algorithm gets the sum of these weights, right? So algorithm wants to maximize the sum of the weights in the final matching. We compare the performance of algorithm to the profit. So profit in this case knows all realized weights in advance, so it can really pick the best matching, the best feasible set. And then we want to achieve as good approximation to the profit as possible. It's a very standard online algorithms paradigm. Well, since it's so closely related to online algorithms, I should actually go over lots of work in online matching. So it actually has a lot of connections to online matching. So for our community, the really most well-known problems are models of online matching and Edward problem. Actually, there has been quite a few papers in EC on Edward problem. So in this setting, we have vertices arriving on one side and vertices on the other side being present in beforehand. So let's say we have a set of items corresponding to the right part of our bipartite graph, and then vertices on the left arrive online. And whenever vertex arrives, we see all the incident edges. So vertices arrive and I reveal all the incident edges to them. Another line of work is it's actually pretty recent on a fully dynamic model where vertices can arrive on both sides. So we don't fix one side in advance. So it will look like this. First vertex on the right arrives, then vertex on the left, then another vertex on the left. And every time vertex arrives, we reveal all the edges to all previous vertices on the other side. So it could look like this. Notice that all these models actually are kind of weaker than the edge arrival model. So results for online matching can be applied to them. And actually in online algorithm literature, there are also many different models about edge arrivals. For example, for the weighted case, unfortunately, you cannot get any constant approximation with online algorithms, so you need to allow some extra power to the algorithm. So namely, preemption would allow you to get some constant approximation in online algorithms. Preemption means that you can take an edge, and then if in the future you get a better edge, you can discard the previous one. Or some probe models where you actually select the order in which you try edges for unweighted case and also get some decent results in this model and so on. So there has been quite a lot of work in the matching, on matching in the online algorithm community. Anyway, so let's return to the profit inequality for matching. So what should we expect to get? So we know that basic profit inequality gives us 50% approximation to profit, and this approximation is tight. So it's actually really easy to translate this example to the bipartite matching. Namely, we have just one vertex on the left and two edges incident to it. One edge having weight, deterministically having weight 1, and another one having really large weight of 100 with probability 1%. So it's like really like, high reward, high risk edge. But in expectation, we're going to get 1 for this second edge. So if we consider optimum, the performance of the profit, it's actually 2 because we effectively get 1 from every edge. So the low probability, high reward edge, it's really takes only 1% of the times, and then we get an expectation 1 from it in the optimum. And in the remaining 99% cases, we get guaranteed 1. But for the online algorithm, the problem is that if we see first the deterministic edge, we cannot really decide what to do properly because we don't know whether we're going to get reward in the future or not. So the algorithm, must, whatever choice it makes, it's just going to get 1 edge. Either it discards this first one or it's going to get deterministic 1 and misses opportunity in the future. So the online algorithm doesn't get more than 1, so that's how we get factor 2. So the question is, can we actually, so what should we expect for the bipartite matching in general? And it turns out that the setting is more difficult, so there is a pretty simple instance to show that you cannot do better than, well, actually, the lower bound is worse than half, so we cannot achieve 2 approximation to the profit. So this instance has 6 vertices on either side, 5 edges. So the red edge is this high risk, high value edge with expected value of 2. There are 2 green edges which effectively are coming either 1.5 or 0 with a coin flip, so it's 50-50. And there are 2 deterministic blue edges with the weight 1. The order, as you can imagine, is of course coming from like higher probability edges to lower probability. So we start with the blue edges and then go to the green, to green edges, and finally to the red. So profit doesn't care about the order of arrivals. Of course, it would try to take red edge whenever possible, so it would get in expectation 2 from it, but most of the times it would be 0. So then we would go for the vertices 1 and A, and for each of these vertices we would choose either green or blue edge. So if green is 1.5, then we take it, and it has a possibility 1/2. If it comes out 0, we take blue edge, which is 1, so with probability 1/2 we get 1. So since there are 2 vertices, 1 and A, we get factor 2. So that's how we get 4.5 for the profit. So best online policy actually should discard the first blue edge, 2 blue edges, because they're going to be a better opportunity in the future because we will get the red one. So it's a good idea to discard them. And then the best thing to do is observe the first edge. If it comes up, tails, if it's 1.5, we should actually take it and the next green edge. So we should accept the guaranteed price of 1.5 and the coin toss for the edge 1B. Otherwise, if the weight of the edge 2A is 0, we just reject both green edges and take the final red edge no matter what. You can do the math, and with probability 50%, we're going to get the red edge, which gives us 2. With remaining probability 1/2, we're going to get guaranteed 3/2 plus the bet on the coin toss for 1B. So overall, we get 2.125, which is by more than factor 2 smaller than 4.5. Anyway, so in our paper we actually get a bit better lower bound with a similar similar instance. So the online policy cannot beat profit, and the profit will get an expectation at least 2.25 of the policy. Okay, so what should we do for the algorithm? So actually, in the previous work, KW and FGL, people found out that a really good strategy is to use fraction of the expected contribution of element to the optimum. So it's pretty good idea to get small approximations. And also they used additive threshold rules. So KW used adaptive prices to compute optimal continuation given the current history, and FGL just used static prices. So what we do in our work, we actually look at extremely simple class of strategies. So we call them vertex additive policy, which is the following. So we fix two price vectors for the left side and the right side, and then we accept edge whenever the sum of the prices on the ends of the edge is lower than the weight of the edge. And we use non-adaptive prices. Okay, so the main result of our work is actually that you can find such a non-adaptive online policy with expected value of at least 1/3 to the profit. And also you can compute these prices efficiently. Okay, just one slide giving you a quick overview of the analysis and how to get this thresholds. So of course we built a lot on the previous work of FGL and KW. Well, of course we get something that resembles a lot KW thing, and well, so, but it's actually a bit subtle because instead of putting thresholds on the edges, we do them per vertex, per constraint in the matroid. So it actually requires subtle handling. Then we adjust analysis for arbitrarily price vectors and get some complex min-max constrained by linear optimization. Well, it involves matrix for the probability and expectation matrix of the profit. We relax this problem to be linear optimization. We implicitly try some solution given by a system of semi-linear equations such that the mean part becomes constant, so it becomes just maximization problem. And finally, we actually give solution to this system of semi-linear equations via gradient descent algorithm. All right, I want to conclude with a list of open questions. So it's actually interesting to look at to get the tight profit inequality for the bipartite matching, and also I hope I convince you that non-adaptive online policies are extremely simple, but also they're pretty powerful. They give good approximation guarantees. So it's interesting to ask what happens for the non-adaptive online policies in other settings. And finally, to study other online models, because profit inequality usually looks at elements arriving one by one, but we can look at many other online settings where maybe vertex arrives and we see many edges, or we do probing models where we actually look at the edges. Okay, that's all I have.